Welcome. Previous class I have discussed about introductions part of nuclear magnetic resonance, that is NMR. So we have seen that for for a nuclear active, that is NMR, this is based on that nuclei of an atom. So based on nuclei, actually we will see that whether particular atom is NMR active or not. Okay, so for that what we have seen that we look that mass numbers, and that mass number is not divisible by 4, then that type of nucleus are NMR actives, and if it is divisible by 4, then that type of mass number, that type of atoms are NMR inactive. Okay, so that types of atoms we will not get the NMR data. And for getting a sharp signals, we see that the second condition, that mass number should be the odd number. If it is odd number, then on that case we are getting the sharp signals, that is spin that is equal to half, that we have discussed in the previous class. So for getting a sharp signals, then we have the two conditions, that mass number that is not divisible by 4 and mass number should be a odd number. Okay, so these are the two conditions we see that, and if it is divisible by 4 completely, then that is totally NMR we will not get. Okay, and if it is not divisible by 4 but it is even number, on that case we will get the NMR data, but that signals are not sharp, that is a broad signals, and because it is a broad signals, then it is not useful to characterize the structure of a molecule. So for getting a for characterizing any NMR data of any atoms, what any molecules, what we have to look that mass number of that atoms has to be not divisible by 4, and that has to be odd number. On that case only we will get a good NMR signals and good NMR data. Okay, so these are the two conditions we have seen in the previous class. So today I am discussing on further from what we have discussed in previous class. So we have seen that 1H NMR and 13C NMR and fluorine NMR and phosphorus NMR. So these all are satisfying these conditions, that is 1H NMR, we see that mass number. So here only we look that mass number. So these mass numbers are all, if you divide by 4, then that is not divisible. Okay, and next condition is that is odd number. So these all are odd numbers. So you will get a sharp signals in NMR data. And if it is like carbon 12, so here this is 12, that is divided by 4. So if you divide by 4, then we are getting 0 remainder. So this is completely divisible by 4. So here that we will not get NMR data. This is nuclear inactive. So that we have discussed in the previous class. Now also we see that in the lab only we will get this type of NMRs. This type of NMRs. Why? Because here only we will get sharp signals. So that is useful to character. That is useful information we get. So this type of NMRs we generally get in the chemistry lab. Okay, so now these are the introductory parts. So in these chapters we are looking for 1H NMR. 1H NMR. We will discuss detail about 1H NMR, and in next chapters we will discuss about 13 NMR, we will discuss about fluorine NMR, and we will discuss about that phosphorus NMR. So basically that if you clear about 1H NMR, then these NMRs are very easy to understand. So first we will discuss detail about 1H NMR. Okay. So first this 1H NMR, we see that this mass number is 1. Mass number is 1. So first divide by 4. So if I divide by 4, then we see that here I am getting 1. So remainder is not 0. So it is not divisible by 4. And we see that this mass number is 1, and 1 is also a odd number. So here we are getting a sharp signals. Okay. So these all these two conditions are satisfied here. So this type of NMRs is generally present in almost all the chemistry labs. and this is the basic NMR. This is the basic that nuclear magnetic resonance, that is NMR, to determine, to characterize the structure of an atoms, of an molecules. In 1H NMR, first we will discuss about of that number of signals. So basic things, basic introductory part I have already discussed from that. So same things is applicable for 1H, that is applicable for all the NMRs. Okay, so this is applicable of 1H NMR also. So the same things, that whatever I say, that nuclear active, all these things. Okay, so now I'm without delay, I'm going to move to the topic, that is number of signals. Okay, so number of signals means how many different types of protons are present in a particular molecules. Okay, so here we are discussing about of the protons. So 1H NMR means we are discussing that how many types of protons are there in a molecules. Let's say if we have the molecules like CH3, CH2, Cl, this we can write these molecules. Now have to calculate that how many different types of hydrogens are present in these molecules. Okay, so that things, that is that whether this hydrogen, this hydrogens, this hydrogen, these hydrogens are same with these hydrogens and same with these hydrogens, or these all are different. So that we will look that. So accordingly, if these are same, then give that one signal. If they are different, they give the different signals. What I mean? Let's, I'm rearranging it. If the molecules is like this, then we are going to discuss that how many signals we will get from these molecules. Okay, so now that it will comes to our mind that here the three hydrogens are same, because this carbon is attached with the same hydrogen atom. So here we look that the environment of this is same. This is also attached to carbon, this is also attached to carbon, this is also attached to carbon. Okay, so these three are look same, and this carbon is attached to another carbon. Okay, now this these carbons and these carbons, they have the same environment. This carbon attached to this hydrogen attached to carbon, and this hydrogen attached to carbon, and this carbon is one side it is attached to carbon and other side it is attached with chlorine. So these are different than this. Okay, that we see what from this observations, what we found that these three are same and these three are different. So what we say that this 3H will give one signals, and this 2H will give one signals. That's what we observe from here. So this way, this is the basic way, that by looking the environmental conditions, we will say that whether these hydrogens are same or these hydrogens are different. But this way we cannot always use this concept, because some complicated molecules will come, then on that time it will be difficult to characterize by looking at that environment. So what we see that we have that three terms. First term is homotopic terms, another is enantiomers, and third one is diastereomers. So homotopics means that is same types of protons, same type of protons, and if same types of proton means that will give one signals. So if they are same types of protons, they will give one signals. And enantiomers, this is also same types of protons. Same types of proton means they also give that one signal. And diastereomers, on that case, these are the different types of protons. Different types of protons, and they give that more than one signals. Means how many different types of protons are there, that type, that amount, that number of signals you will get. So more than one signals you will get. Okay, so now that question is, how will you distinguish which is homotopic, which is enantiotopic? So what is the difference between this? What is the difference between this? Okay, so generally what we see that homotopics are, these homotopics are what they are, here we will do that through axis of symmetry. If we rotate, if we exchange, we get the same protons, then that is homotopic. So for homotopic, what we see that if we, so here we look that through axis of symmetry. Through axis of symmetry, if we exchange the protons, then after exchange, if you get that same protons, then that is homotopic. And for enantiomers, here we look through the plane of symmetry. Plane of symmetry. Here also we look through plane of symmetry. This we look through axis of symmetry. This we look plane of symmetry. What it is? Here, if through plane of symmetries, if it is reflects through plane of symmetry, if reflects, then this is enantiomers, that will get same signals, and this is if bisects. This is if bisects, then that will get the different, so that will get the different signals. So that's how we look. So if we apply this concept to here, so let's say if I'm looking that for homotopic, what we look that axis of symmetry. So if I look that axis of symmetry, and if I rotate this 3 hydrogen atoms, I'm looking for 3 hydrogen atoms. This one I will not look. So these 3 hydrogen atoms, if I rotate through axis of symmetry, let's say if I apply that C3, if I rotate it, then what we see, this will be easily exchanged because these all 3 are same. So these are the homotopic. Okay, and for enantiomer and diastereomers, what I looked at, if we pass a plane of symmetries, let's say if we pass here plane of symmetry, then if we pass that plane of symmetry here, and if these are reflects, then they are enantiomers. If they are not reflect, then they are diastereomer. If it is bisect or not reflect, then they are diastereomers. Okay, that is the theoretical way. So this is the theoretical way, and another way that we always use, that is on the basis of asymmetric center. Generally, whenever you look that homotopic, enantiomer and diastereomers, you will look through the asymmetric center or chiral center. This is the theory part. So if you ask any questions, then we can say the answers like this. But whenever you are calculating whether this is same signal, whether this is different signals, or I mean that it's whether it is homotopic, enantiomer or diastereomers, we will look by the help of asymmetric centers. How we will look that? Let's say if we have the molecules, I'm taking the same molecules, H, 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 CH, H and H. So we will look by the concept of asymmetric center. So what do you mean by asymmetric center or chiral center? Asymmetric center or you can say that is chiral center. So you always use this concept to look whether this is enantiomer, whether it is diastereomer, whether it is homotopic. Okay, this is the very important points, very important words. So we use this concept. We will look at whether it is enantiomer, whether it is the diastereomer, whether it is homotopic. So a chiral center means, let's say if you have the carbons that environment are different. Let's say if we have here Br, here we have Cl, here we have H, and here we have that CH3. So through this carbon center, what you say that all the three atoms, all the four atoms are different, then this is chiral center. Okay, this carbon is chiral center, that we know. Let's say if the atoms here H, but here Br, here Cl, then this carbon is not a chiral center because two atoms are same. So all the four atoms are different. On that case, that is a chiral center. This is a chiral center. Okay, this is chiral center or asymmetric center. So for that, all that atoms presents, all the atoms that chiral carbons, let generally you look at chiral carbon. So all the chiral carbons should be different. That all the atoms attached to this carbon, if are different, then that is asymmetric center. Okay, so now if you are applying to these molecules, here what we see that these atoms and this carbon. Okay, so in this carbon, whether any chiral center is present or not. Okay, so here we see that this I am erasing. So note that for first is let's say enantiomer versus diastereomers. Right here, first is enantiomer versus diastereomers. For this, what you look, you use the chiral center. Okay, on the basis of chiral center. On the basis of chiral center or asymmetric center. What we will look at first, is there any chiral center is present or not? The starting compounds, whatever given in the questions, this is given in questions. So without modifying, what we look that without modifying, how look whether any chiral center is present or not. Look chiral center present or not. So if we look here, then these atoms all three are same, so this is never be a chiral center, and here also same atoms are there, this will also never be a chiral center. So one thing we will get that if there is a no chiral centers without any modifying, then this never be a diastereomer. So for diastereomers, a chiral center should be present. So without modifying, if chiral center absent, then non-diastereomer present. Non-diastereomers. So here that diastereomers never be present. So that it may be either enantiomer or maybe homotopic is present, but diastereomer is not present. So for diastereomers, without modifying anything, there should be a chiral center. Okay, but here there is a no chiral center, so there is chance of diastereomer is absent here. Okay, so here is no diastereomers. Okay, so for diastereomers, first condition is that has to be a chiral centers in the starting compounds without any modifying. Now I will look that whether here any homotopic and enantiomer. Okay, now that homotopic versus enantiomer on the basis of chiral center. Okay, so for homotopic and enantiomer we will do the modifications. Okay, so first, without modifying, no chiral center is there, so diastereomer is the chances of diastereomer is finished. Now we will look that by modifying. Okay, so now I will modify it. So let's replace this hydrogens with, let's say, deuterium. Then what the molecules look like? So CH CH H H. Here I will replace the D, and here it is H, and here it is C. So now after modifying, is there any chiral center is present? So here that chiral center, here I not did any modifications. Okay, so here I did the modifications. So here any chiral center is present. Let's see that all the atoms are different or not. Here, here, here. So all are different. For this case, so this is a chiral center. So this carbon is a chiral center, and if it is a chiral center, we are getting after modifications, then this carbon is a enantiomer. These two, after modifying, if you are getting a chiral center, then these two hydrogens are enantiomers. Okay, so after modifications, if you are getting a chiral center, then that is a enantiomer. Next, for homotopic, what we look here also we will do the modifications. Let's say if I am doing this here, this is not a homotopic, this is enantiomer. Okay, for homotopic, what we say, let's say if I replace any of it, I am replacing with this or anyone. So I replace with this. So with deuterium, these atoms will look, this is H, this is D, this is H, this is C, this is H, this is H, this is Cl. Okay, so now after replace, now I will look that. So I am now looking on this carbon. I am not looking this carbon because after replacement also I get that chiral centers here. So this is enantiomer, it cannot be homotopic. For homotopic, what we look, that if we replace one atom, so I replace this with deuterium. Now look that whether here any chiral center we are getting or not, this carbon. Okay, in this carbon, whether you are getting any chiral center or not. So here what you see that these atoms and these atoms are same. So, and this is different and this is different, but these two are same. So it never be a chiral center. So it can't be a, this is again a chiral. So after replacement also, if you are getting that, if you are not getting a chiral center, then that carbon is, then that hydrogens are homotopic. Okay, so we understand the points. That is first for diastereomer, what you say, without modifying if chiral center is present or not. Okay, without modifying, if there is no chiral centers, then that is cannot be a diastereomer. Okay, and for enantiomer and for homotopic, after modifications, if you are getting a chiral center, that is enantiomer, and after modifying also you are not getting a chiral center, then that is a homotopic. So these are homotopic. Okay, after modifying also we are not getting a chiral center, so these three are homotopic. And if these three are homotopic, then this will give the same signal, that is one signal you will get. Okay, and after replacement of one hydrogens, we are getting a chiral center. So these are enantiomer. Again, so enantiomer also same signals. So these two hydrogen also give you the same signals. Okay, so now that thus both homotopic and enantiomer, we are getting that they are both giving the same signal. So why you are studying homotopic and enantiomer differently, that we will discuss after this. Okay, so now we understand that which is homotopic, which is enantiomer, and which is diastereomer. Okay, this is the basic concept for diastereomers, enantiomers, and homotopic. I erase it. So what we look so far? One is for diastereomers, what we look, that is without modifying chiral center present, then that is diastereomers. And second is after, this is without modifying. And for homotopic and enantiomer, after modifications. After modifications, diastereomer, if you get, sorry, after modifications, chiral center present, then that case, that is enantiomers. And after modifying also chiral center absent, that is called diastereomers. Sorry, that is homotopic. These are the conditions for enantiomer, about homotopic and enantiomer, and for the diastereomer. So diastereomer is without modifying. Chiral center is present, then diastereomer. If it is absent, then there is no chance of diastereomers. Okay. Now the questions is, now we will move. We will look to the examples and we will solve whether this is diastereomer, whether it is enantiomer, whether it is homotopic. So accordingly, how many signals we will get. Okay. So first examples is this. In these examples, what you see that CH3, CH2, CC there. So first condition is without modifying. Look that whether any that is chiral center is present or not. So here chiral center can't be present because these 3 H are same. Here also this 2 H are same. So here also chiral center is absent. So here we will look this all are different. So here is a chiral center is present. So this carbon is chiral center is present. So here is the chances of diastereomers. Okay. Now what we look that, so this one I can write. So this is a chiral center. Okay. So now that if chiral center is present, then this is the diastereomer proton. So this give the different signal. And if asymmetric center or chiral center is present, then next to it, or if after chiral center we get, then whatever in the next atoms we will look at here. You see that this is enantiomer accordingly, because if you replace one, then you will get the different signal. So this is enantiomer. But if that a chiral center is present next to it, or if a chiral center is already present in the molecules, then that enantiomers, all enantiomer will become diastereomers. So these and these will give different signals because a chiral center is present. So after a chiral center is present, then all enantiomers will become diastereomers. Okay, but this is a homotopic. For homotopic there is no any change. So this is homotopic, again it is remain as homotopic. So that is the reasons we will study that homotopic and enantiomer. This is the reasons, because for homotopic also you are getting same signals, for enantiomer also you are getting same signal. So but why you are studying homotopic and enantiomer? The reason is, if a chiral center is present here, so this is give the different signal because this is the diastereomers. After that, this is enantiomer. If there is no any asymmetric center if there is no asymmetric center, then this is enantiomer. But since here that asymmetric center is present, then all enantiomer become diastereomers. So this also give different signals, this also give the different signals. But homotopics give the same signal as it is. It will have no effect of asymmetric center. So here how many signals you will get? For 3 hydrogen, this and this give the same signal. So this give that one signal, and for this we get one signal, 1H, one signals, and for this we will get the different signals. So this 1H we get that one signals, and this H another one signals. Okay, so total how many signals we will get? 1, 2, 3, 4. So total 4 signals we will get. Okay, so here likewise we can calculate the number of signals in a particular molecules. Okay, so moving to the next questions. In these examples, what you see that first we will look at that is chiral center or asymmetric center. So if we look at chiral center, then here there cannot be a chiral center because this is without modifying. We will look at chiral center. Okay, here no, here also can't be, here also no, here also no, here also no. So here we see that there is no chiral center is present. Okay, so no chiral center is present. Okay, so now if there is a no chiral center, then this, if you write this one, then this is look like this. Okay, so here that there is no chiral center is present, so all enantiomer will be enantiomer and all diastereomer will be all homotopic will be homotopic. Homotopic will always remain as homotopic, that is not affected by chiral center. Okay, so here chiral center is absent, so these are homotopic. So this 3H also, here we see that this is also homotopic, this is homotopic, and this is also homotopic because this 3H. Okay, how you look whether it is homotopic or enantiomer? By replacement. By replacement, if you are getting a asymmetric center or chiral center, then that is enantiomer, and after replacement also we are not getting asymmetric center, then that is homotopic. Okay, so you can practice it. So if you replace also we are not getting a asymmetric center, means this is homotopic. But if we replace here this H with D, then we will get that asymmetric centers, means this is enantiomer. Okay, so this 3H and 3H total is 6H. So this 6H we will get one signals because all are homotopic. Okay, and now this 2H, this is enantiomer also same signal. So this 2H and this 2H, sorry, We can't, because this is different 3H and this is different 3H. So we have to write this 3H, we will get 1 signals. Okay, and for this 3H we will get another 1 signal, because this 3H and this 3H is different. So that's why this 3H is different. So for this 3H we get 1 signals, and for this 3H we will get another 1 signals. Now this 2H, after replacement of one hydrogen, we will get a that is asymmetric center, chiral center. So these are enantiomer. So since there is no chiral center in the compounds without any modifying, so there is no chances of diastereomers, so only enantiomers are there. So this 2H, for this 2H we will get 1 signals for this 2H, and these 2H are different, and this 2H we will get another 1 signals. So total how many signals we will get? 1 2 3 4. So 4 signals we have. Okay, so likewise we can say that how many signals are present in a molecules, means in NMR data how many signals we will get. We will get that 4 signals we will have. Okay, similarly this is the one molecules. Thus same way we see that this also we can write that same way, that is CH HH CH HCO. Here also you can write the same things. Okay, so here we see that for this 3H, this is also, first we look at whether asymmetric center is present or not. Okay, so here that no chance of asymmetric center, because all the cases here too, means in the one atom all should be different, we know that. So that is absent here, so chiral center is absent, so here there is no chances of diastereomers, so all are can be enantiomers or homotopic. Okay, so here this 3H is homotopic, so this is get 1 signals, and for this 3H this is also homotopic, so 3H also 1 signals, and this and this, so this 2H 1 signals, and this 2H 1 signals. But if you notice that, so accordingly you say that 4 signals we will get. But if you look that carefully, these molecules here, if you pass a plane, then these and these will be reflect. Here 3H, here 3H, here 2H, here 2H. So if you pass here plane, then this will get reflect with this. This is the mirror image of this. So if any POS is there, then they will give that same. Means this 3H and this 3H, this give whatever the signal it will give, the same signal it will give. So instead of this, we write here that 6H will give 1 signals, and this is the same, because plane of symmetry is there. So this is not give different signals, they give only same signals. So this is 4H will give 1 signal. So total we will get only 2 signals. Okay, so you look that if plane of symmetry is present, if plane of symmetry is present, means they will give the same signals. This and this give same signals, and this give same signals. So if you write, then that we can remember, past we will look whether plane of symmetry is present or not. Okay, plane of symmetry. If plane of symmetry is present, then they will give that 1 signals. After this, what we will look, that homotopic. Okay, this homotopic always give the 1 signals, so that is not affected by asymmetric center, that is not affected by a chiral center. So homotopic always give 1 signals. Okay, this you will look. And third, what you look, that if any like these molecules, if any that CH molecules is there, so that will look that If CH molecules, they will give that one signals. That we will look after questions. And now after that, what we will look? We will check that asymmetric center. Okay, asymmetric center we will check. If after modifications, oh sorry, not asymmetric center we will look. If it is present, then all enantiomers are diastereomers, and they will give that different signals. And if it is absent, then all enantiomers are enantiomer, means all enantiomer are enantiomer. Okay, enantiomers are remain as enantiomer, and that is same signals we will get. Okay, so this is the way we look. First we will look that because POS is present, on that case this will give that same signal. So whatever this will give, this gives. So this is totally 6 signals give 1 signal. Okay, first we will look that POS, plane of symmetry. After POS we will look that homotopic. Homotopic always give the 1 signals. It is not affected by whether chiral center is present or not. Okay, so we will look that homotopic. After that, if this type of molecule is there, then if this type of proton is there, then this is always give a different signal, so that you give 1 signal. After that we will look that asymmetric center. If asymmetric center is present, then all enantiomers act as a diastereomers. Diastereomer means different signals we will get. Okay, and if it is absent, then enantiomers remain as enantiomers, means that is give that same signals. Okay, that's we will look in these examples. So first thing is we look plane of symmetry. So here plane of symmetry is absent. Okay, next we will look for homotopic. So we see that this carbon here 3 hydrogens are there, so this is the always homotopic. Homotopic means we write here this CH3, this is always homotopic. Okay, so this is homotopic, and they will give that 1 signal. So this is homotopic, and this is also homotopic, and this is also homotopic. Okay, so this give 1 signals, and this gives the 1 signals, and this give the 1 signals. That I understand from here. Now this CH is there, so this type of CH I am talking about this subset. So this give that 1 signal, this is give the different signals, that is 1 signal. Okay, from here I understand that how many signals I should get, 1 2 3 4. I will not apply this. Okay, now after that I will look that asymmetric center. Asymmetric center. Okay, so here any asymmetric center is present or not, that I am going to check now. Okay, so here we look that here asymmetric center never be, and here also. So that for asymmetric center or chiral centers, we know that should be a sp3 hybridizations. That asymmetric center should be a sp3 hybridizations. So we can't check here, this is not sp3, this is sp2 hybridizations. So that should be sp3 hybridizations, means that all should be single bonded. Okay, this is the sp3 hybridization. Okay, that is sp3 hybridizations. So this one we can check, this, so this can't be, so this is the only one chance. So if we look here, then I can say that this and these are same, because both the case is carbon carbon. Okay, so this one also we can write like this, CH, instead of CH3 I can just replace this as H. Let's say I am replacing with H, CO, CH3. Okay, so this one I can write, sorry, we can't replace with H because here also H is present, so let me replace with D. Okay, so now that without any modifications, is there any this is H, is there any chiral center? So here we see that same things is present, so it can't be a chiral center. So without any modifications, chiral center is not present. So if chiral center is not present, then there is no chance of diastereomers. Means enantiomer after enantiomer, means these two are enantiomer. These two are enantiomer. So if these two are enantiomers, means these and these are enantiomer. Enantiomer means they will give that one signals. So this 3H and this 3H, total is 6H. This will give the one signals. Okay, and this hydrogens will give one signals, and this is homotopic, so this will give 3H will give one signals. So totally you will get the 3 signals. Okay, so here we will get the 3 signals. Same way another examples, if I look here, if we look in these examples, first we will look check that whether POS is present or not, that is plane of symmetry. So here we look that plane of symmetry is absent. Okay, so next we will go for plane of symmetry is absent. So next we will look that all CH3 are homotopics. CH3 are homotopic. So this is homotopic, this is homotopic, this is homotopic, and this is homotopic. That means that for this I will get one signals, and for this I will get one signals, and for this I will get one signals, and for this I will get one signals. Okay, and this CH, okay, here CH is not there, so I am talking CH means this CH means this type of CH. Okay, so this is not there. So now from this information what I said that these 4 are homotopic. So this get one signal, this get one signal, this get one signal, this get one signal. So 1 2 3 4. So now this is one signal. So total 5 signals I get only I apply up to these conditions. Up to this I will get only 4 signals. Okay, so 5 signals. Now I will look for diastereomers. So here we will look that any asymmetric center is present or not. Okay, so in this we check that here one side is hydrogen, another side is chlorine, another is carbon, but here that is here we see this carbon is present and this is H, H and H. Okay, but for this carbon, this is CH3, this is CH3, this is CH3. So here carbon is present here. So this is an asymmetric center. This is an asymmetric center. Why? Because you see that one side hydrogen, another side is chlorine, another side is carbon is present, and that is with 3 hydrogen. Another is also carbon is present, but here that with this carbon different carbon is present. So this carbon and this carbon is different. So this is a asymmetric center. So if asymmetric center is present, then what we see here asymmetric center is present, but the thing is what you look here, these molecules, but we say let's say this is H and let's say this is Cl. Okay, here that asymmetric center it is here H, here H, here H, and now here C. So let's I replace with this as deuterium. This is D and this is D. So what we see that this is, although this is a chiral center, but this is a homotopic, means all are. Okay, if you replace any one, then also we will not get an enantiomer, and here also if you replace any one, we will not get that enantiomer, means that diastereomer is only affect to that enantiomer only. But here it looks like a homotopic, means all are same. If 3 are same, or if it is a homotopic, then there is a no effect of asymmetric center. although this is a asymmetric center, but these three are same, so this is look like homotopic. Like if I do here hydrogens, so these are not enantiomer, so these asymmetric centers only affect to the enantiomer, but this is looks like this is a homotopic. If you replace all this by hydrogen, this is a homotopic, so this is not affect to it. Okay, so although here a chiral center is present, but here there is no enantiomer, so enantiomer if it is present then it will affect it, but here there is no enantiomer, so it will not get affected. So if we are getting here, this is one signals, then we will get one signal, so these are homotopic type hydrogens, so this will get the same signals for all the case. So this is 9H, we will get the one signals. Okay, because this is get one signal, this is get one signal, this is one signal. Again this is looks like homotopic. Okay, so homotopic means this, for that also we will get that same signal. So total is 9 signals, 9H we will get one signals, and for this 3H we will get one signals, and for this H we will get one signals. So total we will get the 3 signals. Okay, so likewise we can carry out for we can calculate that number of signals if a question is given. Okay, so we will look that first whether this is diastereomers and homotopic and enantiomers. So for diastereomers, what we look that, so if I look a quick summary, then first we will talk on the basis of asymmetric center. So if it is asymmetric center to the given molecules, okay, if it is present, if present, or let's say if absent and if present. Okay, now if it is absent, then there is no chance of diastereomer, or there is no chance of diastereomers, no diastereomers. So all are if it is enantiomer, then that is will be enantiomer. Enantiomer act as enantiomer. And if it is present, then asymmetric center is present, then all enantiomers act as diastereomers, but it is not affected by asymmetric center on the basis of molecules. And if it is absent, but above that point you will write homotopic not affected by asymmetric center. Only that enantiomer will be get affected by asymmetric center. Okay, this is only enantiomer will get affected. And we know that what is homotopic. Homotopic means that one signal it will get, will give one signals, and if it is enantiomer also will get one signals, but if it is diastereomers we will get the different signals. One signal means same signals, that is one signals. Different signals, that is more than one signals we will get. So today up to this we will discuss in the next class about chemical shift. Today up to this, thank you.